between us. It's getting hard to reach out. Haven't seen you in seasons, but all I hear is your voice. I know my limits, you can break me down, but
good evening and welcome everybody. This is Obi-Wan Pez for NCTM Pachinko. We are going to be talking a bit about Building Thinking Classrooms by Peter Liljedahl. Anybody who is interested, Corwin Mathematics has a publication, has a mathematics. Corwin has a public, what the hell? Corwin has a mathematics publication section. So, Building Thinking Classrooms, this is specifically within mathematics, but it does apply if you can expand it to other subjects. But we are mostly a mathematics education group in here, so naturally we're going to talk mostly about mathematics education. Hope everybody's having a lovely evening. Zach, how's it going? I guess it's early afternoon for you. Right, so we went into chapter 1 a little bit last time. Nope, that is incorrect. It's on one of my dog-eared pages. I know that much. There were a bunch of exclamation points. Ah, not that one. There we go. Got into the discussion about studenting behaviors. That's where we left off last time. So if we reset the canvas, right, this is where we want to be. Oh, I need to import a picture because I saved it from last time. $717, that seems right. Nope. That is an Elite Dangerous picture. That does not help. Curses. Let's see, it was a week ago, right? So that should be like the 14th, 15th? Hey, there we go. Hey, Walking Stick Library. Good evening and welcome. Good afternoon for you. Okay. So this was the idea that we had for what Peter Liljedahl was doing with all of the groups of teachers that he had. He collected data from 400 teachers over 15 years and eventually came up with the idea that we should have 14 particular factors which measure into a student's, or that measure into improving student thinking. So the idea, there, skip that page like 4 times. It's on page 14, ironically enough. So, category 1, what types of tasks do we use? Category 2, how do we form collaborative groups? 3, where do students work? 4, how do we arrange the furniture in the classroom? Number 5, how do we answer questions? Number 6, where, when, and how do we give tasks? 7, what does homework look like? And what does even homework mean? And I'm cut off at 12. Okay. How do we foster student autonomy? Number 9, how do we utilize hints and extensions, particularly by using additional tasks and questions? 10, how do we consolidate or summarize the lesson? 11, thank you, Zach, yeah. How do students take notes? 12, how do we evaluate students? 13, how do we utilize formative assessment? And 14, how do we grade? And the order in which these came is mostly in order to facilitate the 3 major topic groups that he stated. Number 1, was things that are happening in the classroom and to change the culture of the classroom itself. Group 2 has to do mostly with the studenting behaviors specifically. And group 3 was on assessment.
There's more to Spotify than meets the ear. That's because video is taking center stage on Spotify, with over 300,000 video views and 300 million users already watching your favorite podcast. With seamless switching between watching and listening, you can tune in anytime, anywhere. Got a show of your own?
So when we look at these particular sets of questions, activities, etc., that we need to figure out how to change, what to do, something like that. It became clear that, the first and probably hardest thing to do, but the first thing that needs to be done is to change the culture within the classroom itself. So the issue that most of the teachers had was that any sort of updates that they did, any sort of changes that were made, did not affect the overall culture. I had multiple instances of experience with this. As did several of my colleagues. They mostly, changed homework using either ungrading or flipped classroom or various other things, but the students still did kind of the same things. It didn't actually make any effective change. The students were still trying to throw in gimmicks in order to, or still trying to game the system the best they could, to do the minimal amount of actual work, to do the minimal amount of learning in order to get the maximal grade that they could. Obviously, this is not what teachers want them to think about. This is not what teachers want students to do as they go through their entire educational career. So that actually falls under group 6. Where, when, and how do we assign tasks? So, right, so asking questions and how you ask questions and what is provided to the students, and also in some extension to that, how do we answer questions? They both belong to kind of the same category, right? So what are we doing in class? What are we doing in the classroom in order to help the students like get where they need to be, where get the students to where we want them to be. So he says that finding practices that generated more thinking than institutional normative practices was not very difficult. So everybody knows this. Basically, as soon as you get into any sort of professional development, literally anywhere, you start coming up with better ways of asking questions. You start thinking about getting students to think more by using whatever method it is that you're learning about for that day. But typically what ends up happening is either the students, again, will manipulate their way back into not thinking, or the teachers get fed up with the amount of work that is required to keep up that level of questioning and answering, because, again, the students aren't doing it themselves. The students aren't able to, because this behavior has not been fostered for any reasonable amount of time. And there are more factors than just that, right? This is not an end-all be-all. Certainly not exhaustive list of issues that are going to happen. So institutional normative practices being the things we just do by kind of default, and they can be slightly varied from institution to institution, but generally speaking, across the entire country, across an entire state, or across a school district, or even just within one school, or even just within, like, you know, one department, one teacher's classroom, how it's always the same. It could be literally anywhere along there. Institutional, yeah, okay. Now we're thinking bigger structures. So your department, your school, your district, your state, the whole country, potentially the whole world. Who knows? We got to think about all the little things that we do that can prevent student thinking. Normative practices were far from optimal, and there are many ways to enact each of these 14 factors such that they generate more thinking. In most cases, we began our research by enacting a practice that was the exact opposite to whatever the norm was. So, you know, oh hey, we've got furniture that's all lined up in desks, or in rows of desks. Cool, let's do literally anything else. So one of the examples was we removed all furniture from the classroom entirely. Turned out it worked great to help student thinking. It did not do terribly well for the teacher. The teacher themselves was actually the issue here and said, like, yeah, this is not working for me. Having an empty room just, like, throw me off my game. There is one chair, and it is for me. In most cases, research began by enacting a practice that was the exact opposite. If the norm was that students sit, we made them stand. If the norm was we answer students' questions, then we stopped answering questions entirely, and so on. In some cases, this contrarian approach produced the optimal practice, but in all cases, it produced a practice that generated more thinking than the baseline data. So essentially, the idea here is that Liljedahl is saying that the issue is not necessarily always picking the opposite thing, but since their metric was it was generating more student thinking, the thing that really messed or the thing that really generated more student thinking was literally anything else. So whatever your institutional norm is, just change it in some way, shape, or form and keep the students off balance. Not just get them off balance, keep them off balance. Groups of teachers tried each practice for 2 weeks. If it produced good results, they tweaked it, and then the teachers kept going. If along the way we tried a practice that was less effective than any other practice, we just tried something else. After a number of iterations, we would get to the point where any changes we made to the practice made it less effective. So at that point, we called this the local optimal practice. It was optimal for that particular teacher in that particular setting with that particular demographic of students. Although these practices were of interest for teaching in general, they were often intertwined with aspects of the teacher's personality, habits, norms, etc. And what we really wanted were practices that worked for any teacher in any setting. So naturally, change things up, see what's going to work well for everybody, rather than just right. So the local optimal practice you change for every individual teacher, but then we try to figure out on the larger scale what's working for everyone. Why is it that, what is the essentially like what is the least restrictive definition of what you're doing in every possible case? So these local optimal practices would be given to different teachers in different settings, different demographics of students, and see how these work for them. And then there would be 2-week cycles of iterations among those teachers until what emerged was a practice that produced the most thinking and was transferable across teachers, settings, and demographics. We would then give that practice to a new group of teachers to use for 6 to 8 weeks to see if it had longitudinal fortitude and wasn't just something that worked because it was new to students, which again is kind of his thesis at one point, is basically like if your students are mired in institutional norms, literally anything different would be better. Right? If it's new to the students, they will pretty much do better than the institutional norm. And not necessarily literally every case, but they do have some, there is some data to support that, as long as, the students and the teachers are willing to give it an actual shot and not just like, again, game the system. So each chapter in this book generally starts with the issue, which is the institutionally normative practice for that particular factor, and then what the problem is with using those normative practices. Introductory sections are then followed by the main part of the chapter called Toward a Thinking Classroom. So that's, again, his narrative about how they tweaked, how they changed to get to where they're at. So again, number 3, where do students work? Why is it better to have students do this particular thing and how can you then get there from wherever your classroom is? um, and there's a lot of advice for implementing practices. What emerged were a number of what I came to call micro moves. These are little things within the practices that we found enhanced, streamlined, or made easier to implement the optimal practice. These are called micro moves to contrast them against macro moves that are the optimal practices for thinking in the chapter. Not to say they're any less important, but some of these micro moves make the difference between smooth and rough implementation. Each chapter ends with FAQ, micro and macro moves, and a series of questions to think about in order to get things working. If you're reading this book as part of a professional learning community, which I did, if you're in the methods course or in a partnership with another teacher, this section may be for you. If you're reading the book by yourself, these questions can also be used to push you to think more deeply about what you've read in the chapter and how you can translate this into your particular classroom. And each chapter also ends with a try this section where you're provided with some tips and tricks, as well as nix the tricks, as well as thinking tasks that you can use to help initiate that thinking practice in the classroom. Feng Shui would be off? Definitely. I mean, to be fair, the dragon has a lot of room to move in an empty classroom. It's like playing Snake. So, in Chapter 1, what types of tasks do we use in a thinking classroom? So the institutional norm for the kinds of tasks. Again, not necessarily how each of them is implemented exactly, but just what is the kind of thing that you're doing in your classroom. So generally speaking, we're talking about, right, lecture. The model which Peter Liljedahl terms "now you try one," which we talked about last week, where basically you do a lecture or even a mini lecture, but you're basically showing the students how to do something. You give them a skills-based approach and then say, now you try one. So you have outlined precisely how the task works, and then you give them something which basically does the exact same thing, just with different numbers. Now, I am profoundly guilty of doing this, because that was pretty much how my entire career went for 15 years, or like 13, I guess. So, generally speaking, right?
There's more to Spotify than meets the ear. That's because video is taking center stage on Spotify.
You do a lecture. Generally speaking, it is skills-based. You could, in theory, also have a theoretical-based lecture, but most of the time, students aren't going to really get that. They're going to look at it and be like, all right, cool, that doesn't really make any sense, and how does this apply to me? Alright, we have the flipped classroom idea. You watch a video or whatever, the actual like lecture of the problem at home, and then you come to class to practice. But realistically, most of the time when you're doing something that's flipped, you're also kind of going back to this now you try one thing, where like you're just showing, let's do the skill. Ideally, the flipped classroom does move more toward doing a couple of other methods. So you can end up with something a little more theoretical. You are supposed to, at home, watch the video and practice the skill itself. Then when you come to school, there's also... this was becoming increasingly popular. Either project-based learning or inquiry-based learning, where teachers would basically just give the students a project and say, like, here's your goal. Today we're going to ask about, or, today we're going to have you all watch this particular video at home, do some practice, and then when you come to school, you're going to be working on this task, whatever it might be. One of my colleagues was in the, she was lecturing for us to get into inquiry-based learning, or EBL, because she's English. And she was in the anthropology department. So basically, the overarching goal of the semester was that students would research where is a likely dig site going to be based on some other, research that they've done for the first, few weeks or month or something like that. Research where to find a dig site. Research how to get permits and other, legal requirements covered. Come up with a packing list of all the equipment you need. Come up with all of the paperwork to make sure that, you can get people and equipment to the dig site. or you could have it be, locally sourced, which is also more likely than trying to bring in digging equipment from a different country. They usually frown on that, to be fair. And using all, how do you use all the tools that you're going to acquire? How do you cordon off each of the sections in the project so that you can then start cataloging everything you pull from the ground? How do you catalog all of the stuff, and where does it go after you're done? How do you legally take care of it, make sure it goes to the proper authorities and whoever? And then what do you do with your report after? And that included both the academic report as well as the expense report. So this worked super well for anthropology because you have an actual semester-long task that is going to get you in and out of the classroom, in and out of a literal professional site for these people to work on. So it worked really well. And of course, this is a community college, so these students should, in theory, all be over 18 anyway. And they should be able to get themselves, or be able to get themselves to a different country without any sort of legal issues. Right, so then the question becomes, what do these particular tasks do for the students, the teacher, and the curriculum at large? Is it going to be something that is going to further students' knowledge? In other words, again, is this a particular skill, as is usually the institutional norm? Is this going to further is this just going to eat up time? Honestly. Let's see. Liljedahl starts talking about Polya. Do we have a first name on that? No. Okay. Cool. Polya's How to Solve It from 1945. And very little in terms of the skill-based lecture and now you try one methods has changed from 1945 to 2020, when this book came out. I think it was 21. Yes. 21. So 1945 to 2021, essentially nothing's changed, right? It's still almost 80 years on, and we are still doing the same type of things. Overall, right, this still also goes slightly with the idea that we brought up last time, which was that a lot of these mathematical practices and just teaching practices in general come from the Industrial Revolution, where we are essentially trying to build students who are able to be one-size-fits-all assembly line production. I'm going to do my part this year for this class, and then they're going to move on to the next teacher who will do their part for that class of students. Again, same deal. They just do their job and then move them on to the next section. It is pretty much literally an assembly line of education. And so the idea here is, again, this doesn't really work. It does not really serve students or the teacher or the curriculum in terms of, particularly, it makes a lot of this routinization again, this is a thesis. This routinization, or we might call it now algorithmization, causes imitation, not creativity, when it comes to problem solving. That's okay. was worried it might be the music might be a little loud, but maybe that's just me. And specifically, in order to highlight this, he says that problem solving is not the precise application of a known procedure. Right, and let's see. Right, problem solving is what we do when we don't know what to do, at least with any precision. Right, we may very well have some ideas, but we don't necessarily know precisely how to get from point A to point B, from a question to an answer. Once that path is known, then it becomes a routine. But if we don't routinize this particular process, whatever it might be, before giving the problem to the students, then they can engage in actual problem solving. So consider the following task. Which is greater, 8 or 9? Right? You may be thinking this is not a good task. And if this question were posed to 9th grade students, you would be correct. That is the wrong audience for this task. But if the same question were asked of a 4-year-old child, this turns out to be a very good task. The strategies that a child would need to invoke in order to figure this out are both complex and nuanced for their particular for their particular routine that they have, for their particular brains, for their particular state of mind, and would require a lot of thinking to resolve. So the question is not whether which is greater is a good task or not. The question is, what is it good for? The answer to that question that it is good for getting students for whom the relative cardinality and or positionality of a number of number symbols have not been yet routinized to think. So getting that particular audience of students to think, it's actually a pretty decent question, even though, again, which of these following numbers is greater would not be a challenge to anybody who had been trained in that yet. Obviously. So for good problem-solving tasks, normally what we're looking to have students get is first stuck. We want students to get stuck because just being able to come up with an answer is kind of boring. And again, doesn't really get them to think, doesn't get them to learn, not truly. So we want them to get stuck, at least a little bit. And based on that, we want them to think, to experiment, to try stuff, to get stuck again, to apply their knowledge, and then probably this application is going to get them stuck in new and different ways, and or to get them to think again. There's going to be a lot of other stuff that's going to we could hook this in many different ways, but generally speaking, right, this is going to be what we would want them to this is kind of what we would want them to do. Again, get stuck, think about it for a while, experiment with some of their ideas, and then try something, and then that trial can get them stuck again, or it can get them to say, I think I've got it, and then apply that knowledge somewhere else, and that application can go back into any of these other states. Most of the times, again, they go and get stuck again, either because they found a new problem that is novel, exciting, and can't be whatever you just figured out can't be applied to that new problem. Or it can be applied but in nuanced ways, or, right, and there's like hundreds, if not thousands of different things we could try and say about this and try to get where we try to get them to get this knowledge and then routinize it themselves, rather than us specifically doing it for them and saying, here's the routine you need to work on. It's more like, hey, here's a problem, see what you think, and get them to work on it a bit, and then try to figure stuff out for themselves. And eventually, there are a couple of methods in particular that we will get to a bit later on, that help out with what do you do if students are now becoming bored because they're just getting the same types of problems over and over again, or they're getting frustrated because their attempts are not working. So either, generally speaking, the two states that get students away from thinking are going to be either boredom or frustration. And we can talk more about that when we actually get to those sections. Right. Problem-solving tasks are often non-routine tasks because they require students to invoke their knowledge in ways that has not been routinized yet. Once that routinization happens, students then mimic rather than think for themselves. And that's where Lithner, 2008, comes up with the phrase that I used before there, being, sort of paraphrased, being imitative rather than being creative. Good problem-solving tasks are also rich tasks in that they require students to draw on a rich diversity of mathematical knowledge rather than, again, just one single skill, for instance. Again, Good task is not what it is, but rather what it does. And if it makes students think, it is going to be a good problem-solving task. So a good problem-solving task will get students to that location. Think often. Okay, so Peter still believed, despite some experiences in one of the classrooms that he was observing in as a, I think, master's student, he still believed that the best way to get students to think was to give them a task that would motivate, even necessitate them to think. And for that reason, he spent a lot of time searching for and designing tasks that would do just that. So he started a collection of what he called highly engaging thinking tasks, and added to this collection mathematical card tricks, and developed a genre of real-world problem-solving tasks called numeracy tasks. So, for these highly engaging thinking tasks, generally speaking, right? The ones that were the best were ones that invoked or like kind of essentially compelled people to think. So people just cannot resist thinking about it. Hopefully they have broad appeal, can be used across a wide range of grades, some being used all the way from grade 4 up through college level. And at first I thought they were rare, so rare that for a long time I didn't even know if any existed. And then I found one, and another, and then several. And now I realize that they are plentiful if you know where to look. So one of the examples that he gives provided that I'm doing this correctly and not just rushing a horrible picture. Right? You go up to the you go up to the chalkboard, whiteboard, whatever you got at the front of the room, or you get the projector to project this. Right? In primary school, again, mostly because these are students who have never heard this problem before, have never been really exposed to this kind of level of thinking. How many squares are in this diagram? right? So here we see that in primary school you get students to think how many squares are in this picture. Most of them will probably answer 16. Fair enough, right? Most of the time they're going to do that. But then you might get the one student who thinks, hey, wait a second. Like, the whole thing is a square, isn't it? So it's not just 16 little ones, but there's one big one there too. Okay, cool. Anybody else have another one? Right? Anybody else have a different answer? Get them to come up and outline each of the individual squares with whatever marker you've got, right? How many squares are there? Now, if you get students who are in a slightly more advanced level or a slightly higher grade than primary school, you could also say, well, what patterns do you see here? So you're going to see, we've got 16. Okay, cool. What sides are those? Well, those are all like one unit, whatever this is, right? Maybe you have to label that at some point. So you say, like, this is 1 unit. Maybe you call it an inch, maybe you call it a meter, maybe you call it a mile. Doesn't matter. But you tell them, okay, this is 1 unit, so therefore we have 16 1x1 squares. Okay, and then we're going to say we're going to add that to how many 2x2 squares are there? Oh, I didn't even think of the 2x2 squares. Or maybe you just say, okay, we've also found... This is one of my favorite things to do. Leave a nice, big, tempting, empty space in between. And say, cool, so we've also found a 4x4 square. And then they look at it and go, huh. Well, I guess that means that we're going to also find 2x2s and 3x3s. So then how many of each of those do we get? Right? And you get them to think through, where do the 2x2s come in? All right, and how many of those do we have? Well, we got 3 going across the top. And then if we shift down one, we got 3 more there. And we shift down one, we got 3 more there. All right, so that's also, if you think about it this way, right, we've got 1, 2, 3 going across and 1, 2, 3 going down. So this is 3 times 3, or 9. This was 16. This was 4 squares by 4 squares. Or 4 squares going across and 4 squares down. And then here we've got 9 2x2s. And if we go 3 across, then we've got 1 position here and 1 position there if we move over. Going down, we got 1 position here and 1 position here if we move down. So this is 2 times 2, or 4 3x3 squares. So we get the sizes down here. And then the number of each size above it. And again, this is there are 1 by 1 of a 4 by 4 square that we can make. So then it's just now, well, what are these numbers? Hey, look at that. Those are the sums of the first 4 squares. So 16, 9, 4, 1, which is going to be 30. right? What if I showed students a chessboard? Here's an extension, right? So now we've discussed how we find the numbers of squares that were in a 4x4 grid. Well, now I say, what about the chessboard? How many squares are on it? And now, okay, this is becoming routine. Now we know that what we need to do, really, is to find the sum of the first n square numbers. Right? And if this is something that is for like older grades, students that are in pre-calculus, right? Again, you give them the earlier task, how many squares are in this thing, with the knowledge that they're going to get this done in like no time flat, or like 5 seconds later they'll be like 16. Psh, easy. And then again, you invite them to look harder. You get a different number. You figure out that your neighbors have a different number than you do. Well, how'd that happen? Think deeper, right? And then once we get into the whole thing, we could say like, okay, we want the summation, if you've done summation within pre-calculus, of k goes from 1 up to n. We're summing up the square of those. Wait a minute, no. K. We're summing k squared. And then maybe some of them will find, hey, there's a formula for that. In theory, hopefully they haven't looked it up on their phones or whatever. But, you know, even if they did, this is a good exercise for students who didn't know this yet. Right? The sum of the first k squares. What was this? n minus 1 and, or k minus 1 and, no, it is n. n minus 1 and 2n minus 1 all over 6. I think that's it. Nope, m plus 1 and 2m plus 1. So, close. Still over 6, though. Right, and now, pre-calculus students could use this to come up with the values up above to make sure that is, in fact, true. Right, if it's a 4x4, we end up with 4 times 5 times 8, 9, all over 6. Take out the 6, we get 3 off of this one, 2 off of this one, and we get 2 by 5 is 10 times 3 is 30. Bingo. Right? 8 by 8. Again, they would have figured this out by just summing up these values, but then we could do, okay, this is 8, 9, again over 6, and 16, 17. Gross. 3 from here and a 2 from here. So this is now 12 by 17. All right. Ads are about to start. Everybody go stretch your legs, cycle that water, grab a drink, grab a snack, whatever you need to do. See you back here in 3 minutes. Thank you for coming. Hey, Phobos. Well, thank you for sticking around. Cheers, Street. Thank you. Trying to remember when I actually had that done. Now I can't remember. Might have been a short while. But yeah, oh, no, right. Let me tell you, this one was a story. So I went to this place and like got my hair cut. It's the same place I've been going to for, I don't know, 3 or 4 times in a row, and their card reader's broken, and I'm like, I don't carry cash. Nobody carries cash. So I'm like, look, I'll go and find cash, and like I had my backpack with me, and I was just like, I'll just leave this here. I'll be back in a bit. And he's like, oh yeah, no problem. I mean, like they don't necessarily know who I am or whatever, but like I go there, so it's not like I'm just in town for the, in town for a holiday and then I'll disappear and never come back. Like they know who I am. I'm the American. So I get in there, or I walk out. I go and I know where there is a cash machine, but I don't know where the nearest cash machine is. So I'm just like, whatever, I'll go to the one that I know. And so I go, they got like Virgin Bank. It's, what's his name? Branson. Charles Branson. Richard. Not Charles. Richard Branson. It's the same Virgin Mobile, Virgin Atlantic, like all that stuff. That's him. So I got to the ATM machine and like I put in my card and I'm like, this probably isn't going to work here. And it was like, they don't accept Discover, which is one of the ones that I just have. Because it pretty much doesn't work outside of the United States, and it doesn't work in most places in the United States either. That's always been the joke. And then, like, I tried putting in my ATM card, or my credit card, which credit cards are awful, right, in terms of, like, borrowing money from ATMs, doing cash advances. Don't do it if you ever carry a balance. Definitely don't do it. But, like, we never carry a balance anyway, so whatever, it doesn't matter. So I went to the ATM, I put in my bank card, and I was like, or I put in my other credit card for here, and I was like, I don't know about this. And I typed in the PIN number that I think it is, and it was like, nope. And I'm like, yo, all right, give me that back. I'm not gonna lose my card over this. And so I went online and like hunted down for, I think I was trying to look up Citibank and like where on the website I could go to Citibank to introduce a PIN, because my Discover card has a PIN. So I was like, all right, this is probably fine. So I put in the Citi card, and I was like, I can't find it anywhere, but let's try this PIN number. And it was like, no, that's not it. And I'm like, all right, give me it back. And finally, after like, I don't know, half an hour of standing on the street wearing essentially this, right? So I've got a t-shirt and shorts on. I'm in the shade in weather that is under 70 degrees, because it hardly ever gets up to 70 degrees in Yorkshire, especially that early in the morning. And I'm just like, come on. Finally get out my bank card for Monzo, which most Americans have probably never heard of Monzo, but it is a um, international bank that like you can use it pretty much anywhere. So, so I break up my Monzo card and I look it up online, and yes, it has, or I look it up in my app, and yes, it has the PIN number that I thought it was supposed to be. So I was like, I should have done this first. Plug that in, and it worked fine. I got some money out and went back, and they were more than happy to give me the, you know, amount of change that was necessary or whatever. I was like, all right. Oy, it took far too long for me to do that. Yeah, Discover's fine, but again, if you ever travel internationally, it's just like it's never going to be accepted. And most places in the United States, Discover is the one that they will be missing if they are going to be missing one. I know American Express, generally speaking, is also kind of on the outs now, I think. I don't know why. So yeah, we were discussing so-called highly engaging thinking tasks as defined by Peter Liljedahl for building thinking classrooms. When doing his doctorate, he was trying to figure out how to get students to improve their thinking skills, and attempted to follow a list of 14 factors that improve student thinking. So we're looking at number one here. What types of tasks are we using? Realistically, this is in order to change classroom culture so that we're not just doing the same old thing that we used to do, and therefore same old thing that we're going to keep doing. It's how do we actually get change in the classroom to get students to think better, think harder, think longer. So I had said that in primary school, he lists this particular problem, right? How many squares are there here? And again, in primary school, even in some earlier level algebra type classes, you're going to see the answer of 16, done. Right, but then we suggest, oh, well, who else has an answer? Is there an answer that's different than just 16? Some people may say, oh, cool, 17. And as I said here, you weren't here yet. Oftentimes what I really like to do just to mess with people is put like 16 here, and then put a big gap in here, and then put +1. And if they don't get it, be like, okay, so why would I do something like that? Oh, well, these are like, where are the 16s coming from? Oh, that's 1 times 1, you know, size 1 by 1 squares. Okay, we got 16 of them. Cool, where's the 1 coming from? Well, that's the 4 by 4, the entire thing. And leave them apart from each other on the list so that they go, oh, huh. I didn't think about the stuff that's in the middle. So the 2 by 2s and the 3 by 3s end up having these amounts to them. And then again, the easy way to figure this out is to say, okay, how far can you move those 2 by 2s? Well, if you got a 2 by 2 here, we can shift it over 1. That's a different 2 by 2. And then shift it over 1. That's a different 2 by 2. And then we're done. And then if we go to the next row, that's down. How far can we go down? Well, where we started, shift down 1, shift down 2, and then we're done. So we've got 3 this way and 3 this way. Hey, that's 3 by 3. That's 9. And it's interesting that the sizes end up being essentially complementary, if you will, to the number of squares they contain. Right, so then we do this, we add them all up. Oh, look, we get 30. Cool. As an extension, okay, what about a chessboard? How many squares are on it? And they might figure out, okay, we do the same thing. This is how many we get, and then we can add them all up and get whatever 12 by 17 is. 12 by 15 is 180, is it? Right, that's 14. 2 by 1 and 7 is 9, that's 10. And then 1, 1 plus 1. 204. Right, because I said 180. Hang on. Not quite. Oh, plus 24. Yes, okay. We're good. Yes, so this is 204. Right, and it's 12 fewer than 216, which is 12 by 18. Okay, cool. Right, so you wouldn't bring up summation notation or coming up with a formula or something like that to like, you know, literally primary school students. But this would be something that you'd want to yeah, I know, right? Oh man. Yeah, 51. 51. So yeah, you wouldn't bring up the formula or the summation notation or anything like that to students at a primary school level. You probably wouldn't even necessarily, well, I mean, coming up with the concept of we're summing the square numbers because they are the numbers of squares we can make of these appropriate sizes might be fine depending on what students you have, what level they are, etc. But like if you're doing this with pre-calc, you can expand it much further than just how many squares are in this 4x4 grid. Right? We can do a lot more with the pre-calculus level student, even though it at the first, you know, sight this says give this to primary school students. Like, you can extend this as far as you want. I'm pretty sure I did this with my calculus students at community college. So, like, you know, these students are 18 to 25, generally speaking, and have already had pre-calculus, and most of them have even had high school calculus. It's just that, oh, well, we got to take it at the college level too, or I didn't learn it well enough, or whatever other reason. My thought was you could also extend this if you get bored with it. Now granted, it doesn't do the same thing, at least not exactly. But if we were to copy, paste this down here. Right, if we were to paste this down here and then do that, and then say, okay, now how many triangles are there? Right, this is less mathematically interesting just because, again, it doesn't follow a nice pattern like the ones up here, right? We're not going to be able to say, oh, look, this is just the sum of the following types of numbers or whatever, right? This is a nice type of problem that has furtherance in whatever class you might be doing. So I had suggested this particular diagram to the group that I was doing professional development with at my community college. The two ladies that I had gone to Toronto with were also in this keynote, and were also super excited about this particular thing. One of them bought the book while we were there, as I did, had it shipped back to our school while we were out, so that it was waiting for us when we got back on Monday. And we almost got stranded in Toronto. That was great. Actually, it might have been New York. Either way, it was less amusing. Yeah, so I had suggested, oh, well, why not do something like this? But I don't think I really thought it through. Again, the other one is you can now develop the sums of squares formula. You could develop, if you're in a discrete structures class, you could develop the idea of proof by induction. You could come through and say, well, how do we know that this is true? We could even get a student to look up the formula of the sums of squares and then say, how do we know that this is true? And then go from there to say, well, if we were to take the sum of squares formula, and now how do we prove rigorously that this is actually correct, right? A discrete structures class, even maybe a pre-calculus class, would be able to go through that and say, if we were to show that it works for any of the examples we have here, then that's cool, but it doesn't actually prove that it works forever, right? But we can do, if it works for n, then we can show that starting from n, it'll work for n plus 1, and therefore this whole thing will work for any value of n that we give it. And again, this particular thing, it's kind of I hate to say it, but it's kind of an intellectual dead end. I've made that claim about non-common core, not all, but several non-common core arithmetic topics, particularly like multiplication, addition, subtraction. Yeah, addition, subtraction, multiplication. They're pretty dead end. The division algorithm can be used later on for algebra, as we've seen in this stream. That we can do polynomial long division and then synthetic division to find zeros of polynomials and all sorts of cool stuff like that. But in terms of trying to figure out, like, when are we going to use the division algorithm outside of that, that's less useful. Okay, so highly engaging thinking tasks. The other one that he gives for intermediate buy a game for $10. Sell it for 20. Buy it back later for 30. Later still, I sell it for 40. What's my cash status? So, not really. Yeah, not really that, but how much did I make or lose? You made a headache. Yes. Look, these limited edition limited edition NES cartridges don't come along every day. The original Bubble Bobble, yeah. All right. The NES Gold Zelda cartridge, yeah. We had the original gold cartridge only for Zelda 2. I don't know why exactly we bought the Zelda 2 game and never actually bought Zelda 1. I think maybe I was excited because it was new or newer, something like that. And it's a very different game if you were expecting the other one. But that is the one that Zelda 2 is the one that I learned how to play like most NES type stuff on. Which one was Manhandala? Is that the one with the mouths on the orthogonal? Yeah. Nice. So middle school, I have a 4-minute egg timer and a 7-minute egg timer as hourglasses, i.e. they have sand in them, and they do actually measure 4 minutes and 7 minutes.
Between watching and listening, you can tune in anytime, anywhere. Got a show of your own? Upload your video to Spotify, turn views into fans, and monetize your passion.
Can I cook or time a 9-minute egg? I know, they have a spring in them, and you turn them, and then they go tick, 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 and then when they get to the end, they go. That's what egg timers do. Or I suppose they look like an egg, and then you twist them like that. I actually have my boarding passes from my trip to Toronto. They were used as my bookmarks in this book. Well, the ones with sand are just little miniature hourglasses, which are the kind that you would use for, like, Yahtzee or something. Not Yahtzee. Pictionary. It's a Pictionary timer. Zach, I can count on you for that one. You were putting both of them together. Okay, fair. Right? So this one, if I have a 4-minute egg timer and a 7-minute egg timer as hourglasses, i.e. two different hourglasses with sand in them, can I cook or time a 9-minute egg? And how long are they going to need to wait until they put the egg in, based on the number of times you've had to flip over hourglasses? Because again, here you can flip hourglasses at various moments, but one of them must run out each time you flip. That is the deal. So if we flip over both of them at the same time, right, the 4-minute will run out, but the 7-minute one will be only partially through, and then you could flip both of them again, and now we get different amounts of times that we can actually time. For intermediate, this is actually not terribly difficult, right? This is just a matter of students thinking about the money that's coming and going and what exactly is happening with all of it. There's going to be somebody who's going to come up with the correct answer, which is just that, well, every time that we do this, we're gaining $10. And that's it. So we've done it twice, so we're up 20. Somebody might still want to be like, well, I just earned $60, so like... Yep, that's the same as like the water buckets to make 4 gallons when you have 2 different sized ones, whatever they are. You want to make 4, but you only have like a 3 and a 5, or two very different sized ones. couldn't resist thinking about it, you said. And then the high school problem. An eccentric woman has booked 3 adjacent and adjoining hotel rooms. For the sake of argument. When she checks in, she tells the receptionist that if he needs her, she will always be in the room next door to the room she was in the night before. The receptionist doesn't think anything of it until an hour later when he realizes that her credit card has been declined and must now go find her. The problem is that he is so very busy and only has time to knock on one door per day. How many days does he need to guarantee that how many days does he need to guarantee that he finds her? And then what if we extend this to n number of rooms? And p number of days. Is he going to be able to find her before she ends up leaving? And Peter's other highly engaging thinking tasks include any sort of math-based card tricks, including the, like, deal out 9 cards and then you pick them up in rows, or in columns, rather than laying them, as you laid them down in rows, you pick them up as columns, and then you can always pick out which card somebody chose by telling you which row and which column it was in, separately. I'm explaining it poorly, but I think you all have seen stuff like that. And then numeracy tasks. So something like right, a ski trip cost given a certain number of constraints. He did a ski trip fundraiser as one of his examples here. The idea is that every student in the class, or every student intending on going on the trip, raised a certain amount of money. There is a rental cost associated with each person, depending on how much equipment they already have at home. There is a lift ticket, and there is a lesson cost, depending on whether or not the person's going to take it. Lift ticket is constant for everybody because they're assuming that they're just going to have to pay that anyway. And here he comes up with 3 vocabulary words. We have a low floor task. right? All learners may end up finding a point of entry, which may be different based on experience and perspective. So each individual person might be able to find a completely different way of getting into the task. We also have a high ceiling task. um, there is enough ambiguity and room for extensions that you could keep the conversation going, or you can introduce variations of the same ideas, yeah, room for extensions. So generally we call this like evolving complexity. Right, and then lastly we have open middle. So these are three definitions of numeracy tasks, or three different categories of numeracy tasks that Liljedahl introduces during this particular section. This is, we have a single final correct answer, but there are multiple ways to approach and solve. So many different approaches and methods work just fine. Right. Even if there is a rich task that maps nicely onto the curriculum you're trying to teach, it may only map to curricular outcomes if students happen to solve the problem using concepts and skills from their current curriculum. So this, this is the nature of open middle and open-ended tasks. I guess technically open-ended would be another possibility, but generally speaking, right, he doesn't explicitly define it, but an open-ended problem has no real end to the problem itself. It's just going to keep evolving every time that we think we've got it pinned down. Something else ends up happening where it's just not done. And he discusses non-curricular tasks as well. Does not map onto the curriculum for that particular class at that particular time. You know, it might end up that this is something that is found later on. And oftentimes, I would find myself foreshadowing something that would come in the future, and then being like, oh, but let me tell you, we'll come back to this in, you know, a couple weeks and discover a new method or a different way of looking at this problem or something like that. That could always be fun. It's kind of interesting if you can get students to start thinking about things that are, down the road, because in some cases, a few of them would be interested enough that they'd start researching or attempting things on their own, completely independent of class, and be like, so hey, what about this? Right, so this is the nature of open middle and open-ended tasks. Such tasks invite students to think for themselves, and when they begin to think for themselves, a lot of unpredictable things can happen, which I can definitely, absolutely 100% say happens all the time in, real classrooms. Just even doing my like Socratic dialogue that I did for almost every single year that I taught every single class, discussing things with students in real time always yielded interesting side roads and diversions that would get us onto discussing something that oftentimes ended up being super rich. And a lot of times I would come up with, oh hey, here's an alternate way to prove whatever it is that we were trying to look at. I think we were looking at trying to find the proof of the law of cosines or something like that. And, it's got a pretty steady, pretty rigorous proof that you have to follow. And then somebody asked me a question about something, and we started exploring this alternate way, which ended up getting us to something different and something interesting, but it wasn't like the law of cosines. We weren't quite there. Yeah, there were other examples like that where we went off on tangents and found some cool stuff, and it turns out that it's not entirely useful, but at least it was something interesting that we could discuss. If your goal is to use a rich task to, for example, get students to think about division of fractions, then this could be a problem. Of 30 students, only a handful may choose a solution path that ends up following the lines of the curriculum you're hoping that this rich task would touch on. So that's my example. We start going off in this tangent, we end up discussing something completely different, or even if it is the right thing, it certainly is not the way that I expected things to go. The rest of the students in the class may end up using repeated subtraction, repeated addition, a type of logic that makes unnecessary the need to think about fractions at all. And depending on the grade you're teaching, these solution paths, although not achieving what you were hoping for, may still touch on the topics from the curriculum. More often, however, this is not the case. If, in reaction to this, we try to force a more predictable curriculum by artificially constraining the tasks, before long we have reduced what was once a rich task into the type of word problem we often see in textbooks. Camille went to the store to buy eggs, milk, and cheese. Eggs cost this. Milk cost this. Cheese cost this. How much money did she need? Word problems, like rich tasks, require the student to decode what is being asked. However, once a word problem is decoded, the mathematics is often trivial, procedural, and analogous to the mathematics that was taught that exact same day. This is not true of rich problem-solving tasks. Once the language has been decoded, the mathematics that is needed to solve is neither trivial nor procedural. Basically, in rich tasks, the problem is in the mathematics, And in word problems, the problem is in the words. This is why maybe they're called word problems. And whereas rich tasks get students to think at the expense of meeting curriculum goals, word problems more predictably and reliably push students to use specific bits of learned knowledge, but often at the expense of engagement and the thinking that we're trying to foster in the first place. So when we move to toward a thinking classroom, although seemingly unrealistic, one way forward is to stop worrying about curriculum. Oh, that was in the book. That was right there. Yeah, I'm like quoting pretty directly. My earliest efforts to build thinking classrooms did just this. Forget about the curriculum. Like, you have goals, but like, don't think really highly about what you're trying to do. Rather than think about curriculum, I was only concerned with getting students to think. This is not to say that I was only concerned with getting students to think. This is not to say that I was naive about the lived reality of classroom teachers and the present, persistent and ubiquitous nature of curriculum. Rather, it's just that I needed to start somewhere. Before I could begin to think about how to get students to think about curriculum, I needed to get students to think, period. This proved surprisingly easy. Once we shed the burden of curriculum, it turns out that there are a huge number of resources available to us that are effective for getting students to think. From problems of the day to brain teasers, the internet is full of resources that are engaging and thought-provoking. Some of these, it can be argued, address curriculum, but again, only for those students who follow a particular solution path. Students, as it turns out, want to think and think deeply. My efforts to building thinking classrooms, early efforts to building thinking classrooms through the use of highly engaging thinking tasks, card tricks, and numeracy tasks, and my cavalier attitude about curriculum were actually hugely successful. Successful to the point where I could give a teacher a set of 3 tasks and, without any changes, could dramatically increase both the number of students who were thinking and the number of minutes that were spent thinking. On top of that, students were enjoying and looking forward to mathematics and the next task. Their self-confidence and self-efficacy increased, and they became better mathematical thinkers generally. The trick, the issue at hand, is trying to maintain the positive effect and positive affect while turning our attention back to the reality of curriculum. So to do this, I had one thread to follow, the thread that comes from understanding that problem solving is what we do when we don't know what to do. Curriculum tasks are typically the exact opposite of this. Curriculum tasks are often what students do when they know what to do, after they've been shown how. So asking a high school student to factor a quadratic or an elementary student to solve addition of 2 numbers with decimals after they have been shown how promotes mimicking, not thinking. We've discussed mimicking before, last curriculum chat that we had, and also, we didn't, a little bit today, but my observation of those initial 40 classrooms showed that this is exactly when and how curriculum tasks were most often used. Having said that, it turns out that both of these questions are excellent thinking questions if they're asked before the students have been shown how to answer them. Herein lay the root of how to get the students to think, while at the same time addressing grade-specific curriculum. So, for example, let's look more closely at factoring quadratics and how that question can be presented without first teaching students how to do it. Okay, let's start with a bit of a review. How would I expand x plus 2 times x plus 3? Teacher writes that on the board. Students, x squared plus 5x plus 6. Teacher writes on the board, x squared plus 5x plus 6. Okay, so if my answer were x squared plus 7x plus 6, what would that question be? So we've done it forward, but now how would you do it in reverse? How would you figure it out? The goal here in this one would be, let's do the AC method, right? So we can split the middle term into two parts, make it look like an expanded binomial multiplication, and then put it into the binomial parts, right? How do we do that? And then we'd figure out something from there. In my case, I would probably do as I have been doing for the past 15 years, which is taking that middle term, split it into two pieces, and then do grouping. So factor by grouping to make sure that we get the same factor in both pieces that can then itself be factored out. So it's a double factoring greatest common factor. Right? Adding decimals. Let's start with a brief review. Can someone tell me what 3.1 means? Oh, that's a number that's bigger than 3 but less than 4. Okay, is it closer to 3 or 4? It's closer to 3. Okay, what about 5.2? It's a number between 5 and 6 that's closer to 5. Okay, so if I add 3.1 and 5.2, what two whole numbers is the answer between, and which number is it closer to? What would the answer be? And even counting could be turned into a thinking task. Let's all count up together to 20. Complete that. Okay, what if we start at 14? What are the three numbers that come after 14? And what are the three numbers that came before it? These scripts are similar in that they begin by asking a question about prior knowledge, then they ask a question that is an extension of prior knowledge, and they ask students to do something without telling them how. And as such, they require students to think not only in general, but also about particular curriculum. It turns out that almost any curriculum tasks can be turned from a mimicking task into a thinking task by following the same formulation, by asking a question that is review of prior knowledge, then asking a question that is an extension of prior knowledge. In my research, I compared 3 types. So I will write that up in the break. Gonna have ads here starting in just a few seconds. And thank you everybody for coming. Be back in 3 minutes. Get up, stretch, grab some drink, snack, whatever you need, and be right back.
When your kid's favourite toy starts to run out of battery power, no need to worry. Your new batteries are already on their way, arriving today with Prime. Everyday essentials delivered fast. It's on Prime.
I'm Professor Huggington, and I like to hug.
Cut-off times and T's and C's apply. See product page when ordering.
There's more to Spotify than meets the ear. That's because video is taking center stage on Spotify, with over 300,000 video shows and 300 million users already watching their favorite podcast. With seamless switching between watching and listening, you can tune in anytime, anywhere. Got a show of your own? Upload your video to Spotify, turn views into fans, and monetize your passion.
All right, welcome back, everybody. So, the three types of lessons that he compared were the non-curricular tasks. So, type 1. We discussed that earlier. Highly engaging, card tricks, numeracy tasks, etc. No regard to curriculum whatsoever, just fun, exciting, get kids to think. I am using kids here very generally, but he was studying specifically K through 12, so the label pretty much applies. Type 2, scripted curricular tasks. So as stated in the quadratic and addition task that we were doing before break, you go through a script, we talk about how these things are related to mathematics, and we also run something forward or run through the lead up to a particular problem and then just let them go at whatever it is that it was we were intending on doing. In the case of quadratic, again, this was okay, first we know how to expand stuff, so now if it was a different problem that was already expanded, how do we factor? It's the reverse. And then the third is as is curricular tasks, the stuff that is already being done in most classrooms. Direct instruction promotes students to mimic what the teacher is doing rather than necessarily think about what is actually going on with that particular problem. Okay, so this is like the absolute best part of this chapter. You can tell because I put exclamation points next to that chapter heading, or next to that paragraph. So, quoting, there were big differences between how students performed in these types of lessons. Although the first two lesson types were both designed around tasks to get students to think, the lesson that was designed around non-curricular tasks got many more students to think than the lesson scripted to get students to think about curriculum, type 2. Simply turning a standard curricular task into a thinking task was not enough to get all the students thinking. I mean, fair enough, right? Similarly, whereas the second and third type of lessons are both built around curriculum, the lesson where direct instruction was used, type 3, allowed more students to successfully complete the task at hand. This is not surprising, as mimicking can be an effective strategy that allows many students to be successful in the short term. But as mentioned in the introduction, mimicking is not thinking and therefore not learning. Naturally, there are also students who are successful on the rescripted curricular thinking task, type 2. There were just fewer of them than with direct instruction. However, an interesting thing happened when the three lessons using non-curricular tasks, type 1, preceded students' exposure to the scripted curricular thinking task, type 2. The number of students who successfully completed the scripted tasks, type 2, surpassed the number who were successful in the mimicking, type 3 lessons. In other words, students can be successful at these types of scripted thinking tasks even more successful than in lessons designed to promote mimicking if their willingness to think is first primed with the use of good non-curricular tasks. So the type 1 tasks are more likely to engage the students with their rich and interesting contexts and then propel them into thinking than a task asking them to think about factoring quadratics, adding decimals, counting, etc. But once the thinking starts, it becomes an end unto itself, and students are not only more willing to think, but they want to think. The non-curricular tasks, type 1 in this regard, served as a primer for, and thus made room for, the more curriculum-driven, scripted thinking, type 2 tasks. Investigation and interview with a student led to, in almost every situation, the teacher was able to predict when the class was ready to shift their thinking toward curricular thinking tasks. Interview with a teacher. Yeah, I don't know why, but they just seemed ready. There was no more whining, and the kids came to class excited about seeing the problem they were going to work on that day. The key was, however, that in the transition from non-curricular to a curricular thinking task, type 1 to type 2, nothing else changed. The teacher posed the task as a challenge, as a problem to solve, without any big declarations about, well, now we're going to move on to what we're doing for today or whatever. We're not going to say we're moving on to today's lesson. It's just, here's a challenge. Go for it. That is not to say all students were successful or that all students were even willing to think. Far from it. Simply turning a basic curriculum task into a thinking task does not mean students are automatically going to think, but more things need to change if if thinking is to be built and sustained over time. And that is what the rest of the book is about. These results show that to get students thinking about curriculum tasks, first they need to be primed to do so by using non-curricular tasks. Nothing in my research has shown a way to avoid this. You have to go slow in order to go fast. And I highlighted in the margin Sunil Singh of Chasing Rabbits said something very similar to this in his book, and yes, those are all of my that's not even all of them. That was like the first half of the book. Those are my tab notes. I had them color coded too. I don't even remember what they are. They're labeled at least, so I'll come back to it. I think green is quotes. Purple is tasks. Then yellow and pink. Yeah. I think yellow is maybe the educational concept. Yellow is also a task. I think that might be more verbal task, whereas the purple ones are like visual tasks. Anyway, Sunil Singh also, I met him during that conference in Toronto. It was pretty great. And actually, I won that book there. We were talking about math history, and he asked a question, and I answered it correctly because I teach math history. Or taught math history, I suppose. Still do it here sometimes, you know. FAQ. In this chapter, as well as the introduction, mimicking is portrayed as something bad. Isn't mimicking a good starting point for the students before moving on to thinking tasks? Well, the question is not whether mimicking is good or bad. The question is, what is mimicking good or bad for? Mimicking is very good at teaching students how to replicate routines. The routine for factoring quadratics, adding decimals, dividing fractions, etc. So good, in fact, that once students start to have access with having success with mimicking, they don't want to stop. Mimicking is an addiction that is easily acquired at lower grades and difficult to give up at higher grades. Ah, guilty. Yup. I discovered in differential equations was the first real class where I had the very large epiphany that, oh, I can't do this anymore. I can't just look at the problem, look at the types of problems that are here in the examples, and then apply them to the exercises. Like that didn't work anymore. It sometimes worked great, but yeah, it was. I mean, it had actually hurt me before that, but I didn't realize it. I mean, realistically, it hurt me all the way back, but it had really hurt me in, I think, mostly Calc 2. Calc 1 was kind of okay with it, because again, we're mostly looking at it and saying, oh, well, yeah, I get it. It's just, there wasn't much of a reach that we were doing from the examples to the exercises. There wasn't a reach. Differential equations usually had a big reach. So this was the first time that it really got like out of hand. Right, you may have seen this when trying to explain a difficult concept, and some of your students are just asking you, just show us how to do it. Yep, I had a lot of those students. The problem is that mimicking is only an effective strategy when the number of routines to memorize is small. As the student moves up in grades, the number of routines per topic increases until this becomes unmanageable and ineffective as a strategy. Yet students who have had success with it in the past are resistant to abandoning it. Aye, that's me. I'm the problem. It's me. Furthermore, mimicking tends to create short-term success without long-term learning. That allows students to make connections with other topics in the same and subsequent grades, so they don't develop the web of connections that helps them understand mathematics. Mimicking is bad because it displaces thinking. Mimicking happens not alongside, but instead of thinking. Likewise, mimicking is not a precursor to thinking. Mimicking requires less energy and less effort than thinking, and once mimicking has begun, it's difficult to ask students to shift their attention onto something that takes more energy, time, and effort. Our research on studenting behaviors and homework showed that only 20% of students who mimicked at the beginning of their homework assignment were even willing to attempt questions for which they do not have an analogous, worked-out example, and that would require them to think. It's me again. And of those, only half of them were able to complete a question for which they did not have an analogous example in their notes. Help. I don't have time to give up 3 to 5 days of my school year to do non-curricular tasks. Can't I just jump right in with curriculum thinking tasks? So starting to build thinking classrooms with non-curricular tasks is imperative. As already mentioned, their use dramatically increases your student success with scripted curriculum thinking tasks when transitioning to those types of tasks. How it does this has not been mentioned. Well-selected non-curriculum tasks with their engaging contexts propel students to want to begin to think. We said that earlier, so. They create situations where every student gets stuck, which makes stuck an expected, safe, and socially acceptable state to be in. In essence, these tasks make it safe to fail and keep trying. And through these struggles, students begin to build confidence in their teachers' confidence in them. And all of these qualities are easier to build inside of highly engaging non-curricular tasks and are necessary when we transition students to curricular thinking tasks. This is not to say that these same qualities can't be built inside of other curricular thinking tasks, but it is much harder, takes longer, and will only work well with a few students. Curricular tasks are too familiar to signal that something has changed, and thereby they are less likely to prompt a change in behavior. Even if I want to use curricular thinking tasks, it will take so much longer to have students think their way to solutions than if I just show them. How am I going to find time for this? There are a lot of aspects of time that came out in research. First and foremost is that the time it takes before students are given an opportunity to answer a question on their own. In lessons designed around having students mimic Type 3, this opportunity does not occur until 15 to 35 minutes into the lesson. When using thinking curricular tasks, this happens in a fraction of that time. Looking back at these 3 sample scripts in the chapter, you will notice they're all very brief. Chapter 6 discusses more about how important this is in terms of minimizing the teacher time in the class. For now, however, it's enough to say that when relying on previous knowledge to prompt thinking, these types of scripts will always be brief. Second aspect of time is how long it takes students to solve a task when asked to think versus when they're asked to mimic. In each of these example scripts, not only is the setup quicker, the students tend to come to an answer much more quickly. This may not be true the first couple of times you design curricular thinking scripts, but it goes faster and faster the more adept the students become at thinking. The script for factoring quadratics, for example, when used in a fully implemented thinking classroom context, will cover the entire unit on factoring quadratics in 40 to 70 minutes. Each of the examples in this chapter drew on prior knowledge. What does it look like when we're starting with an entirely new topic, a topic for which the students have no prior knowledge? Well, curriculum is inherently spiraled, so for this reason it's seldom the case that students have no prior knowledge at all. In the rare cases where this is actually true, you can, if you wish, just tell the students something. But you still only have 5 minutes before you should ask them a thinking question. Take, for example, the introduction to the Pythagorean theorem. I offer 2 different scripts that can be used, the first of which relies on pattern spotting. I'm handing out a sheet with 8 different triangles on it, each with all of its side lengths indicated. What sort of patterns do you notice? A sheet structured as in the above figure would allow students to notice that all the triangles are right triangles. They may also notice that some of the triangles are proportional to each other. They may also notice that extra numbers on some of the sides of the triangles are the squares of the sides that are attached. They may also notice that there is a relationship between these square numbers. Second script involves a more direct approach. If you look at these 3 triangles I've drawn here, you'll notice that they're all 3 right triangles. All right triangles share a property that the sum of the squares of the shorter 2 sides plus the square of the equals the square of the longer side. This is the Pythagorean theorem, written a squared plus b squared equals c squared, where a and b are the lengths of the shorter sides and c is the length of the longer side. For example, we see that in the first triangle, 3 squared plus 4 squared equals 5 squared, and in the second, 5 squared plus 12 squared equals 13 squared. Knowing this, consider this third triangle, where the shorter 2 sides are 8 and 15. What must the longer side be? Although very different in approach, both of these scripts have students doing a question they have not been shown how to do in the first 5 minutes. The first script promotes pattern spotting. The second approach asks them to apply a known property. Regardless, they're going to have to think their way forward. So I run the script, and the students successfully answer the thinking question that I pose. What now? You ask a similar but more difficult question. Entire chapter 9 is written about this, but for now just ask progressively harder questions. For example, in the second script, you may ask the students to answer a question where the two shorter sides are decimals. So 3.4 and 5.2. Ask them to answer a question where they're given the lengths of the longest and one of the shorter, etc., etc. So the macro move is to begin the lesson, the first 5 minutes, with a thinking task. The micro moves are the first 3 to 5 thinking tasks you use should be non-curricular, highly engaging thinking tasks, type 1. After that, do not announce it, but shift to a scripted curriculum thinking task. Script the curricular task such that you begin asking a knowledge question that is prior knowledge, then ask a question that's an extension, then ask the students to do something without telling them how. The book club questions. So what are some things in this chapter that immediately feel correct? I wrote several things like against a couple of these, but not this one particularly. But easing students into something using a more fun task and then just jumping in with a curricular task does make sense, right? In terms of what I had learned from all sorts of other professional development stuff. Like, I had mentioned that pretty much every single professional development that I went to in my 15 years of teaching was in here in some way, shape, or form. But the thing was that this is advocating for using every single one of them in a slightly different way, and all oriented toward the exact same goal. Whereas it was always like, well, you know, we can throw these things in here and just try it out this year and see what happens. And it's like one thing used in isolation. And it never quite worked. It always yielded positive results for a bit, or it always yielded positive results, you know, in some muted sort of way. But yeah, like getting students to at the very least open up to thinking is an interesting way to start your class, even if it is completely and utterly not related. Naturally, we do some cool stuff on like Pi Day or various times throughout the year. In this chapter, you read about the negative consequences of mimicking. Can you think of any positive benefits? And if so, do these positive benefits outweigh the negative consequences? So, certainly with me, right? It was something that I could get through, that I could throw on the board, that I could show my genius to my students, and then get them to essentially be like, here's the process, go to it. But again, like it's not interesting. The students don't like it. It causes them to disengage at a much higher rate. Even if it is something that, you know, literally I did as a student through half of my college career, or pretty close to half of my college career. Right? It was just, again, it's something that was obviously not working. And it took a level of maturity to understand that. So students need to be shown that as early as possible, I think, that, you know, doing this mimicking is really helpful in the short term, but it doesn't actually get you to learn anything. Same with like history, right? If you're spending all of your time and energy in history memorizing names, dates, and places, like half of that stuff is interchangeable. It seems arbitrary. It's just, stuff that happened. Whereas if you learn that, the teapot dome scandal was this thing that was related to this other thing, which was related to this other thing, which was related to this other thing, which went both forward and backward from that moment in time. The effects of it echoed through history, and the reasons that it existed in the first place were etched throughout all of the rest of, that time period. Like, you can learn so much more. It takes so much more effort. But, like, that's history for you. None of my teachers did it, really. Or at least, it never seemed like they were doing that. They might have been, and I just probably wasn't paying all that much attention. The introduction mentioned that almost all students who mimic express that they thought this was what they were meant to be doing. This chapter shares that one of the ways in which students come to this conclusion is by having their teachers show them how to do something before asking them to try it on their own. What other ways may we be communicating that mimicking is what we want students to do, even if that's not what we want them to do? I mean, rewarding that behavior for one. And I was also mentioning, like, I wrote in here that the assessments that we submit are entirely based on, can you do the following thing? Can you perform the following task? So in assessing the students, if you're asking them specifically and explicitly to do a task, then all they need to do is to mimic the thing that they were doing in class. But if you give them much more leeway, it's going to make a much more difficult exam, both to correct and to do. But you might get a much more rich view of how much a student actually knows. So, in theory, we should not be asking students to complete a task for an assessment, but rather start looking at like, what tasks could we get them to do that don't relate to the curriculum directly, but have all of it built in? Again, much harder. And then the next question is, do we need exams? Is that really a thing that's helping us? I know at my community college, we had the leeway to do all sorts of stuff. So, like, you want to change the grading scheme? Sure, let me know how it goes. Like, pretty much all the full-timers had leeway to do whatever we wanted, and then just, go to our department chair and make sure that it made sense, and that there's oversight. And then end of the semester comes, and if it worked, great, write it up. If it didn't work, great, write it up. Explain what we're doing. Explain how you're going to fix this if it didn't work. You've read in this chapter that curriculum is inherently spiraled and therefore have very few examples where you would introduce a topic for which students have no prior knowledge upon which such a script can be built. Can you think of some examples of such a situation in your curriculum? If you can, is there really no prior knowledge that can be drawn on? So, I said that my inclination to run class is Socratic in nature. So I'm starting from known concepts in the first place on almost everything that I do, and then building historical context for whatever it is that we're trying to study. So what we need what I would need to do then is to get the students to see or discover what that next step is, from going from here's your known historical context. How do we then work out the new, the new problem, the next problem? In this chapter, it was shown that students perform better on scripted curricular tasks if they have first experienced 3 to 5 classes of working on highly engaging, non-curricular tasks. How do you feel about giving up this time? What are the barriers for you to do this? What do you stand to gain? What do you stand to lose? The students who were in my classes told me that they were concerned with the effective use of time and that we were missing out on a bunch of stuff. So, yeah, it gets a little nerve-wracking maybe that we're kind of spending all this time on like fun stuff that wasn't explicitly in the curriculum. And by the end of the semester, because it was my first semester running it, we didn't finish the class. We did not actually get to the end of the curriculum, but it was my first attempt at doing this, and I needed to rein in a lot of either non-curricular discussion or like the time that I spent walking around the room asking groups what they were doing, where they were stuck. Maybe you should go speak with that group over there, and we'll talk more about those kinds of teacher behaviors as we go further through the book. What are some of the challenges you anticipate you will experience in implementing the strategies suggested in this chapter, and what are some ways to overcome those? Again, my issue was trying to get the students to see the next step, having the students complain that we were missing out on time, getting students to explain, or getting students to yeah. There was another thing that I was going to put in that space. With my community college students, I literally read a lot of stuff out of these chapters, which it was limited to like a few sentences a day. But it got to the kind of thing where it was like I read out the one that was all about mimicking, and I let them know that in college I was most definitely through college I was most definitely a mimicker, and until I got to differential equations, and always looking for essentially the easy way out, always looking for the answer encoded in a slightly different done example. I was also smart enough to be able to make some pretty easy leaps from not just literally the same problem with different numbers, but like problems that were done differently enough that it would probably confuse several people, that I then was able to say, okay, this doesn't quite line up, but let's try to flex this a little bit so that it does line up better. So I was kind of mimicking plus. And then the try this for this section, and then we're going to probably call it a night. As mentioned in the introduction, the ideas in the first 3 chapters are best implemented all together. So you can ignore this and implement the ideas in this chapter just by itself in isolation. If you're doing this, remember to start with 3 to 5 non-curricular tasks and get students doing these in the first 5 minutes of class. If, however, you are going to heed the advice and wait until the end of chapter 3 to try anything with your students, this is the time to create some of the scripts in preparation for this. This chapter included 3 examples of how to script the introduction of a task so that you can ask students to think their way through a problem without first showing them how to do it. These examples are all predicated on the idea of asking students a question about prior knowledge and then asking a question that is an extension of that prior knowledge. Consider some topics you have recently taught or are about to teach and try to create some scripts for this task. And I should give you all the actual Okay, so here is the book for anybody who is actually interested. You can also just go find it wherever. But that is the Corwin website. They also have a purchase site called Sage. I don't know if that's actually affiliated technically with them or if it's somebody. It doesn't really matter. But I want to keep going with this, and so on next Monday, I think I want to delve into chapter 2, which is on the second part on how we form collaborative groups in a thinking classroom. So how exactly do we go and make the groups that we're going to use? And what are the challenges with making groups? I'm sure you all have, in doing group work, found many different challenges. All right, Dr. Gold is up, doing some tutoring if he's not just about ready to leave, but we'll see. Boop. Yeah, looks like he's doing physics at the moment. Potential energy. So we'll go see Dr. Gold. Thank you so much, everybody, for coming. We do mathy type stuff here on Mondays and Wednesdays, so I will see you on Wednesday for more like problem solving type stuff. Most likely we're going to be starting work out of the Cracking the GRE math test, Princeton Review 2002. It's a source of good problems, what can I say? We are on Calculus 1. So if anybody is interested in bringing any other problems to the table, feel free to do so. We've got plenty of time to spend on whatever we want. And other than that, I will probably be in Dawn's chat tomorrow. Dawn Factorial is going to be doing some I think it's usually math help on Tuesdays and Thursdays. So we'll be back on Wednesday. We'll be hanging out with Dawn tomorrow. And then on Friday, we will be doing Against the Storm again and trying to get over to the gold seal that's over there. It's going to be quite a few streams before it happens, I'm sure. So, see you all later. My name is Obi-Wan Pez. This is N Simplex Pachinko. Have a good night.